Hello everyone, today let's take a look at QP161, another geometric distribution question where we have these three guys, Ty, Guy, and Cy, and they're all flipping these fair coins until they respectively obtain their first heads. So we let T, G, and P represent the number of flips needed for each of them to get their first heads. And then we just need to find the probability that T is less than or equal to G, which is less than or equal to P. So basically what that means, if Ty flips his coin such that it takes him 3 to get his first heads, then we need Guy at least that number, right? So Guy might have 4, let's say, right? And then we need basically Cy to have at least that number. So maybe he gets 4 as well, and then this would be a valid, basically, arrangement. But if it took Guy 2 flips instead of 4 to get his first heads, well, then this would not be a valid arrangement that satisfies this condition right here. So we just need to find the probability of this, right? Some order statistics of the geometric. So we know how the geometric is distributed for Ty, so let's just think about Ty first, since he is going to be our lowest amount of flips that we need, right? So let's say Ty basically has I going from 1. At minimum, he could have 1 flip until he gets his first heads, all the way up to basically infinity. And then his probability of tails on any given flip is going to be 1/2, right? We raise that to the power of basically I minus 1, because we need I minus 1 failures before our first success, which happens with probability 1/2 at the end, right? And since these probabilities are equal, we can just combine this into 1 basically and just say 1/2 to the power of I. So this is basically the distribution of all the possible ways that Ty could flip his first heads, right? And then for each possible number of flips I that it takes for Ty to get his first heads, we basically need Guy to have at least that many, right? So now we can multiply this right here by J going from I all the way up to infinity. And then the probability that basically Guy gets J amount of flips, which is going to be at least I, right? Which is what we need, right? So the probability that he gets at least J flips is just going to be 1/2 to the power of J, some for the exact same reasons as it was back here, right? So this right here is basically for Ty. This one here is for Guy. And now we need Cy to have basically at least the amount of flips as basically Guy had, right? Which we represented by J. So now we can multiply this right here by the sum from, let's say, our next iterator is K, going from J all the way up to infinity of 1/2 to the power of K. So this right here will be for Cy, right? So for instance, if I equals 3, right, then we'll have 1/2 to the power of 3. That's the probability that it takes Ty exactly 3 flips to get a heads. So here I would be equal to 3. This is just an example. And then basically right here, you can see that we're taking J equal to I. So we're just summing up over all the possible values that G can take, right? The number of flips for Guy. And that's going to be 1/2 to the power of 3 or 4 or 5 or anything up to infinity, right? That's why we have that sum there. And then Cy's number of flips, which is represented by K, again, once we flipped Guy and Ty's flips, right, it's going to have to be at least that of Guy. So that's why we start K at J one more time, and then we're iterating over all the possible values up to infinity, right? So that's why that formula is what it is. And now we can just basically start evaluating these sums right here using geometric series, which we proved back in QP64. So we know how to evaluate this sum right here. The first term in this expansion is going to be when K is equal to J, which will give us 1/2 to the power of J on the top. And then by the geometric series formula, again from QP164, we just take that over our common basically factor, which in this case is going to be 1/2. So 1 minus 1/2 on the bottom, which is just 1/2. So dividing by 1/2 is obviously just like multiplying by 2. So this right here will just be 1/2 to the power of J minus 1 in simplest terms. And again, this makes sense right here because Guy's flips we were calling J, right? So this basically represents the probability of tails. We're raising that to the power of J minus 1 because we need the number of flips until the first heads to be at least that of Guy, which means they need to flip J minus 1 tails, right? So now let's just replace this term right here with 1/2 to the power of J minus 1, right? Which we're going to bring inside of this sum here, or it already was inside of that sum. I should have put parentheses. But now 1/2 times J times 1/2 to the power of J minus 1 is just going to be 1/2 to the power of 2J minus 1. And now let's go ahead and just evaluate this sum right here, which we also know how to do because of QP64. Formula for the infinite geometric series is we take our starting element. In this case, our starting element is when J is equal to I. So when we plug in I for J here, we get 1/2 to the power of 2I minus 1. That's the first term in that expansion. And then we take that over our common factor. And what is our common factor? Well, every single time that we iterate this, we're basically going to be multiplying by 1/2 to the power of 2J instead of just 1/2 to the power of our iterator. Right now it's 1/2 to the power of 2 times our iterator. So the formula for the geometric series basically is going to be 1 minus 1/2 to the power of 2. That's obviously going to be 1/4, so 1 minus 1/4 is just going to be 3/4. When we divide by 3/4, it's like multiplying by 4/3, right? So now this is what we have. That is basically what this sum right here evaluates to. So now let's just plug in that. So we have 1/2 to the power of 2i minus 1, and then we have times 4/3 as well, right? So now let's get rid of this, and now we just have to do this final basically term right here. We have to evaluate this. So that shouldn't be too hard, right? We can just pull this 4/3 out. It's a constant with respect to our iterator. And now right here, we can combine these terms because we have this common factor of 1/2, right? So it's just going to be 3i now minus 1. And now we know how to evaluate this. Again, it's another application of QP64, the geometric series formula. We have this 4/3 out front. And then to evaluate basically this sum right here, we take our first term, which is when we plug in I equals 1. When we plug in I equals 1 into that equation right there, we get 1/2 to the power of 3 minus 1, so 1/2 squared, right? And then we just divide that by our common factor, or 1 minus our common factor. In this case, our common factor is going to be 1/2 to the power of 3, because every time we iterate, we're multiplying by 1/2 to the power of 3. So now we just take this over 1 minus 1/2 to the power of 3, which again is just going to be equal to 1/8. 1 minus 1/8 is going to be 7/8. Dividing by 7/8 is just multiplying by 8/7. So now we have a pretty simple formula right here. 1/2 to the power of 2 is just going to be 1/4. So right here, these 4's will cancel, and we'll just have 8 divided by 3 times 7, which is just equal to 8 on 21, which is the final answer. So a pretty simple application here of the geometric distribution, where we're just using the geometric series formula from QP64 for all of this. And the final answer, again, is just going to be 8 divided by 21.